I guess I'm the token industry person on the panel. Uh, Good morning, still morning. I'll try to keep it brief, but the panel is about transformative technologies for a climate resilient power grid. And just wanted to have a concrete industrial level example of how to deploy a technology, how to develop it, but how to deploy a technology to contribute to that. There are many, many layers to this. This is just a little example, but sort of bring it down to tangible field items. One thing I do want to acknowledge, some of the material here has already been published and presented at IEEE and PACworld, which is Protection, Automation, and Control technology conferences. And I will use examples that my collaborators from Luma Energy in Puerto Rico have contributed to, particularly Chevitri Vega and Francisco Rodriguez Colon. Just want to acknowledge that. I'll make some of these brief in the interest of time. The team already covered a lot of the challenges. When you are looking at a climate resilient power grid, aside from the challenges of the climate events and more extreme events, more often events, we also do have aging infrastructure, maybe stating the obvious and the basics, asset management challenges. There's energy transition, electrification of transportation, electrification of many other industries. So more and more is coming on electricity, and to that end, it's making it more critical, if you like. And then you have got, at the same time as everything is affecting the grid, the importance of it, the necessity of it, especially for vulnerable communities, is becoming more and more places. For example, in Puerto Rico, I'm referring to, it becomes certain times of year life critical to have power or not. It is not just about, taking a bit time off. And on top of those critical loads that come addition into the sort of grid, data centers, particularly AI-rich data centers. I was talking to Dominion Power that covers a good part of DC and West Virginia, and they're looking at 30% load increase. So 30% more than what happened over the last 100 years, purely for data centers. They're looking at about 100% load increase over the next 10 years, everything else included. So that is a huge, huge element there. And at the end of that, I think both Ali and Roshi touched on this: affordability, reliability, resiliency, sustainability, and security. All of these, based on interpretation, is still core. Those things are not going away, and those are actually the core principles of all of this. Just looking at an example of how we can use technology to help here. So here we're looking at better visibility in the grid. We'll talk about, for lack of better word, more capable eyes. Better, in this case, voltage or electric field sensors that allows you to see the grid a different way so that you can prepare, respond. Roshi covered all 5 stages of resiliency. This helps at all stages, of course, shortening the recovery, reducing the extent of it, and most importantly, enhancing the grid resiliency after the fact. Okay. So it's not only locating a fault accurately, but also locating little things that later on may become a fault, or under hurricane wind becomes a fault before it happens, and fixing it before. I'll look at an example from Puerto Rico. I won't go through some of these details, again, in the interest of time. From an industrial, practical perspective, science of traveling wave fault location has been around for a long time. This comes about, how can you deploy a practical technology so that actually helps in the field? How can you simplify it that the field folks can actually deploy it in a practical scale, under pressure, under safety concerns, under all those sort of situations? And prime number one in power utility, if you're in research, you might have heard of it or not. First, do no harm. Don't make it worse. Because if you're not careful what you're doing, you can make it even worse. than what it is. So the rule number one is there, and we used basically a technology, optical passive sensors that do not touch any relays, any breakers, any substation critical assets. And in an environment where all of those are extremely fragile, not well maintained necessarily, and have seen hurricanes and tropical conditions for a long time, that is actually a serious thing. You know, you can damage, you can go below where you were. And basically, the technology itself, you can read about it. Don't want to get much into that, but it's an optical sensor system and samples at high frequency, has a few orders of magnitude more bandwidth than conventional current or voltage transformers have, and it can be deployed at ground potential. You don't actually put it on the high voltage, picks up the electric field. And provides the service effectively quickly. 2 hours in and out of substation, that's all it takes to be done without touching anything else. Whereas you want to install a new relay, it's months of planning, studying, testing, all of that. Now, let's look at the deployment. So we want a resilient grid, but you can't have a resilient grid if the controls and the measurements and all of that themselves are not resilient. If during, you know, critical time on the road in big traffic, your eyes and ears shut down, it's not good, right? You know, those need to stay up and functioning. Of course, those feed your brain, and your brain has to make decisions, or if depending on one of these driverless cars, feeds the brain of the driverless cars to do the controls. But all of that, the system that monitors needs to be resilient at certain ways. This is a simplified 230 kV backbone of the Puerto Rico grid. It's about 16 substations and 20 lines, but it's a bit simplified. And we have put sensors only in 7 substations. So 7 half-day trips going there, getting out. And with that, we can say within the tower where a fault happens on the entire 230 kV grid anytime, including when I was sitting there a few minutes ago. It's a tool. Important thing is about it is to be deployable. More important thing about it is to work all the time. And the way it's designed, because you use the voltage traveling wave as opposed to current, where most relays work, if any one of these sensors is not available, the wave still travels to the next substation. That is a backup. That is a grid level redundancy. You don't have to double every device, but you actually use the neighboring device. May not be as perfect, maybe not within the tower, maybe tower and a half, which for all practical purposes is the same location. But that is a tool that helps basically locate the fault. The question is, and I have a bit of pictures so that you can visualize these little sensors you see on the ground side of an insulator, not on the high voltage side. The only thing connecting that to ground is fiber, so itself is safe, easy to deploy. And there is an electronic cabinet which has some basically signal processing, light source, all of those things that are industrially made, and time tagging. So you get actually grid-wide GPS synchronized sub-microsecond time tagging of megahertz resolution, as well as sample values, which are kilohertz resolution, and phasor measurement. My friends at PNNL, different group, but they use a lot of the phasor data. So those are all available from this system. And the emphasis is not on the phasor data and AC, is on really event location. Some waveforms, you'll see these slides. Again, in the interest of time, I don't want to go through it, but the point, the concept of traveling waves, not new. The fault happens, 2-step responses go in 2 different directions toward the 2 substation. You measure the time difference, you would know where it is. The point though is, if you measure it at a typical relay that samples at 10 kilohertz, the very bottom of that, you would know within 30 kilometers or 20 miles where it is. Not very helpful, okay? But when you get to microsecond resolution, because in a microsecond, wave travels about 300 meters. Speed of light, you know, people like to say 3 times 10 to the power 8 meters per second. I like to call it 300 meters per microsecond in a more practical way. So, or 1,000 feet per microsecond. So that's how much it travels. If we have that resolution, you can have that accuracy in fault location, and becomes a lot more practical and useful. An example, fault happens between substation H and G. You can locate it based on time difference between those. I zoom in this waveform, just this little portion. So this is 400 millisecond. I guess that makes it about 24 cycles worth. But if you zoom in a half a millisecond version, you can look at the time difference of those pulses arriving. Traveling wave concept, again, is not new, but implementation is practical quick. It says, hey, it's about somewhere here, it says 9 kilometers from substation G. But imagine the sensor substation G is not available. Same fault, you see waveform substation H and K, and you look at line KGH as a hybrid line. Again, same analysis, same zooming, of course, different time difference, and locates the fault pretty much in the same location. So it's resiliency of the monitoring system at architecture level, as well as the hardware has to be, of course, hard and good. So from an industrial approach, basically, we're looking at a multi-layer resiliency, right? Understanding the grid, got to harden the grid at many levels, deploy a lot of different technologies. This is a little example of, hey, when you can locate the fault. By the way, the same sensors or same technology provides if you have harmonics, your inverters are not working properly. Again, having the wide bandwidth, having the better eyes allows your brain to develop better solutions. Oop, there is a low battery here. I won't go through much more details. I'll leave it for the questions. But again, I emphasize this is just an example. And there are many, many ways to look at resiliency at all different levels.